In this video, we're going to be looking at topic 2E, extraction and uses of metals, in the IGCSE chemistry course for Edexcel. This is a triple only content, so we will be only discussing triple outcomes. So if you are a double student, you might want to check out some of the other videos on this channel. So we're going to be looking at how we extract metals from the Earth's crust and compare both unreactive metals and more reactive metals on how we extract them. We're going to be looking at the methods used and link that to the reactivity series and be able to comment on the extraction process. Please note that the detailed knowledge of the processes used in the extraction is not required. So that is very different to the old specification. The old specification may ask you to give details. So if you are doing old specification papers, you don't actually have to answer these questions. If you're not sure, please check with your teacher. We're also going to be looking at the uses of alloys and what an alloy is and why they are sometimes preferred to metals. So, metals can be found in the earth and they are generally combined with other elements in the crust. So any compound of metals and these other elements are called minerals. And they're typically found in oxides or sometimes in chlorides. And minerals are found usually in rocks, and we call these rocks an ore. So an ore is a rock that contains a mineral in a high enough quantity to make the extraction worthwhile. What you may find is that some rocks contain these minerals, but they're only in very small amounts, so it's not worth the actual extraction process. So we want to use an ore that has a high enough content of minerals. And we extract these metals using various different methods. Now, some metals can be found uncombined in the earth, and we call these native elements. And that just means that they exist naturally as uncombined elements. And these will tend to be low on the reactivity series. So that is because if they're low on the reactivity series, they are unlikely to react with things like oxygen or water or acid. And some examples are gold and platinum, and sometimes you can find silver or even copper, but these two are quite rare to find uncombined. Typically, the most common native element is gold. Now, if we are extracting a metal from its ore, we typically have to separate it from an oxide. So we may have something like copper oxide or iron oxide, or even aluminium oxide. These are the key ones that we're going to look at in this topic. And it is all about how we get the metal from these compounds. So in order for us to remove the oxygen, we have to undergo a reduction reaction. So remember, oxidation is the adding of oxygen. And if we are going the other way and we are removing oxygen, then we call it reduction. If you're not sure about redox reactions, which are oxidation and reduction, you might want to go back and check topic 2D, the reactivity series, and that can give you some more information, or again, ask your teacher. So if we get a reduction reaction happening to remove this oxygen, we must have another substance that undergoes the oxidation. And that means that it will have the oxygen added to it. So that means that the ore must be heated with a reducing agent. Now remember, a reducing agent causes something else to be reduced. And in order for something else to be reduced, it itself is oxidized. So the reducing agent is the compound that is oxidized, and that causes the metal ore to be broken down and undergo a reduction reaction to leave us with just the metal. And typically the reducing agent that we use is carbon. Now, the method of extracting metals from their ores all depends on their reactivity, and it depends on their position relative to carbon. So you have to make sure that you are quite confident in your reactivity series. Again, if you're not sure, you might want to go back and check on topic 2D. Now we've got a picture here, which is some of our elements from the reactivity series. Now there are, of course, more elements in this, but these are the key ones that we have to know. So we have potassium, sodium, calcium, magnesium, aluminium, then carbon, zinc, iron, and copper. If we have very reactive metals like potassium, sodium, calcium, and such, we require very large amounts of energy in order to extract them. And there are two methods of extraction that you need to be able to identify, and that is roasting with carbon and electrolysis. So any metal that is below carbon on the reactivity series, the way that we extract them is we roast it with carbon. So if we go back and we have a look, we do this for zinc, iron, and copper will all be extracted by roasting with carbon. And because carbon is higher on the reactivity series, it is the thing that undergoes the oxidation reaction. If the metal was higher than the reactivity series, the metal would then undergo the oxidation. So we have to make sure that this is only for elements below carbon, and then it will remove the oxygen from the metal. So for example, if we take iron and we heat it in something called a blast furnace, you can see here we have iron oxide, and we're heating it with the carbon. The carbon will undergo oxidation and form carbon monoxide, and we will form iron metal. Notice that it is a liquid, so it is molten iron. This is done at a very, very high temperature. The iron itself is reduced because it loses oxygen to form the iron metal, and the carbon is oxidized because it gains oxygen to form the carbon monoxide. Okay, so make sure you can identify which one is being oxidized and which one is being reduced. Now this is an example of what the blast furnace looks like. So you can see that we have got our iron ore, and we have something called coke. That is just our carbon. And we also add in some limestone as well. And that is put into our blast furnace, and it melts and travels down to the bottom, and through our hot air, and this is all sealed with steel lined and heat resistant bricks. And eventually what happens is we make our molten iron at the bottom, and that is then removed, and we have this part here, which is the slag, and these are all impurities. Okay, and in this case the carbon and the carbon monoxide that is added or that is formed in this reaction act as reducing agents. So these are the things that will take the oxygen and then allow the molten iron to be formed. Now, you are not required to know how the blast furnace works. That is all in the old specification. So again, if you're doing these questions and it's asking you to explain the blast furnace, you do not need to answer that. You can move on to another question. If we have metals that are above carbon in the reactivity series, we cannot use this extraction method with the roasting. What we have to do is we have to do electrolysis. Now, you have covered electrolysis in topic 1E, and it works very similar to the way that you have to do that in that topic, but you're unlikely to be asked about the half equations in this particular topic, but it could link into a question from 1E. So any metals above carbon are more likely to be oxidized, so the carbon wouldn't remove the oxygen as we would want it to. So what we do is we carry out the method using electrolysis. And remember, electrolysis is splitting or breaking down of a compound using electricity. Now, in this case, we would use aluminium, and the aluminium is extracted by an electrolysis of aluminium oxide, and we dissolve it in a molten salt called cryolite. Now, in this case, the aluminium is oxidized into aluminium metal at the cathode, and the oxide is reduced to oxygen gas at the anode. So we have something that acts like this. So we have our cathode, which looks a little bit different. This time it is the lining of our container, whereas the carbon anodes, we have multiple anodes. So we have multiple carbon electrodes here, and these are, as we've said, where we're going to get the oxygen being formed. So when this happens, we get the cryolite salt being used because that actually has a lower melting point than the aluminium oxide, so it reduces it by about 1,000 degrees, which means that we have to use less energy. Now, electrolysis does, however, require very much large amounts of energy, especially in comparison to using the blast furnace. So we only actually extract the metals using this method when we absolutely have to. So if the metal can be extracted by roasting with carbon, then we will always use that method. We only use electrolysis if we have to because it is very expensive. And what you can see happening is the solution, which is your aluminium oxide and your molten cryolite, will undergo the electrolysis, and then we get our molten aluminium being collected at the bottom here. And then after the reaction happens, we can then separate the two and get our molten aluminium, which we can then cool down and use for various different uses. If we shift our focus slightly away from extraction and we look at the uses of metals, and we're going to introduce alloys. So an alloy is a mixture of a metal with another metal or with carbon. So we've got two metals mixing in together, and we can then refer to these as alloys. Please be aware that it is not a compound, it is a mixture. If you use the word compound in an exam, you will lose the mark. So examples of alloys are ones that you've probably come across before. So we have brass, which is made of copper and zinc. We have bronze, which is made of copper and tin, and steel, which is made of iron and carbon. Now, alloys have slightly different properties than the metals that make them up, and typically they tend to be much tougher and much harder than pure metals. Now, the reason that we have this increase in hardness is to do with the way that the metal ions are arranged in the lattice. So we know that in metallic bonding we have cations surrounded by a sea of delocalized electrons. If we have a metal on its own, all of the atoms are going to be of an identical size. If, however, we have an alloy, we are going to have different sizes of our atoms. Therefore, our lattice arrangement is slightly disrupted, and you can see that on the bottom right-hand side diagram. This is where we have our regular arrangement, because all of our atoms are the same, and here we have a slightly irregular arrangement. And because we have this irregular arrangement, it causes problems when the layers of metal are trying to slide over one another. That is what usually makes some metals brittle, is because the layers can slide over one another and then they can move apart. With an alloy, when you apply a force, it's more difficult for these layers to slide, so they are less likely to do so. Therefore, they're not going to break down as much. So they are harder. If we look at aluminium, aluminium is a very low density metal. It is a very good conductor and it resists corrosion, so it doesn't like to be corroded. Please note that we do not use the term rusting. Rusting is only used for iron. If you're talking about the reaction of a metal due to the presence of oxygen and water, you should be referring to corrosion. Now, these are particularly good properties, with them being low density and a good conductor, so we tend to use these in things like airplane bodies or in electricity cables. However, pure aluminium is not very strong. It's actually quite a brittle metal and we can break it. So what we tend to do is we will mix the aluminium with another metal to make an aluminium alloy. That increases its strength, but it still keeps all of these other properties. So we're increasing the strength and maintaining the other properties. So we are improving the aluminium. For copper, it's the same sort of thing. Copper is a very good conductor of electricity, and we tend to use it in wires for our electronics. It is also very unreactive because it's quite far down in the reactivity series. It is ductile, malleable, and has antimicrobial properties. Now, copper typically can be used on its own, but it is also used in alloys like brass and bronze. And again, that just gives them a little bit more strength whilst also maintaining all of these properties here. And we tend to use copper for things like wires to make pots and pans, specifically water pipes because it's very unreactive with water, and we'll sometimes use it for surfaces in hospitals because it doesn't allow any microbes to grow on it. Now, if we look at steel, steel is an alloy of iron. And there are three types of steel. There is mild, high carbon, and stainless steel. And you will come across these pretty much every day of your life, probably the most commonly in stainless steel. So each of these types of steel have their own sets of properties, and therefore they have their own set of uses. And the steel is iron mixed in with carbon. Now, if we have mild steel, we're adding in just a small amount of carbon, and again, it gives it a little bit more strength. And this we use for things like nails, bodies of cars, shipbuilding, and for girders as well. If we have high carbon steel, you can see the amount is much higher. We tend to use these where we really need the strength. And that will be in things like cutting tools and masonry nails. So masonry nails are things like in building sites or to hold structures together. The one that is most common that you will come across is stainless steel. This is where we add in carbon with a bit of chromium and some nickel as well. And we tend to use these in cutlery, cooking utensils, and kitchen sinks. So if you've noticed that your forks and knives and spoons that you use to eat don't corrode, and this is because the iron, in this case, has been treated with the chromium and the nickel to form an alloy, and it gives it the properties of it not reacting with water. So it allows it to not corrode or to rust at all. So we use it for things that are going to come into contact with water. So let's finish off by looking at some past paper questions. What you may find with the old specification is that there are not that many past papers about the extraction of metals that you can answer that are going to link into the new specification. So I've only pulled one or two here, and they're very short questions that are more to do with the uses. So from the 2014 paper, steel is an alloy that contains iron, and there are three differences between steel and aluminium. So steel can rust, but aluminium resists corrosion. Steel has a higher density than aluminium, and steel is much stronger than aluminium. So we want to use this information to explain why, to suggest why steel is the better metal for making bridges. Now, we can talk about corrosion, because that is important, that we don't want our steel to corrode. However, it's not the best answer there. The best answer is linked to the strength. So steel is stronger than aluminium. So because the steel is stronger, we want to make our bridges out of that because, of course, we want our bridge to be extremely strong so that it doesn't collapse and cause any accidents. For part 2, we want to suggest why aluminium is better for making aircraft bodies. Again, you can mention that it is to do with the strength, but steel being more strong probably would be better. Steel does resist can rust, so the aluminium may be linked into the corrosion, but actually it's point number 2 that is the most important. If we want to use something in a vehicle that is going to have to fly, we want it to be quite lightweight. Now, you cannot just say lightweight, we want to specify about its density. So the fact that aluminium has a lower density. We can also mention that aluminium resists corrosion, because of course when you get up into the atmosphere, you are going to have some water vapor, and of course you do not want any rust forming on your airplane, because rust can cause damage to the structure of your plane or your car or whatever it is, any vehicle that you're wanting to use. So if it's a plane and that's going to go into an area where there's water vapor, then it can cause structural damage, which of course we don't want, because again, we would be causing an accident there. So you can see we've got stronger and a lower density or resist corrosion. If we finish off with the June 2012 question, so iron and aluminium are two important metals extracted from their ores on a large scale. Iron is extracted using a blast furnace. Iron is extracted from its ore used by electrolysis, and this is a more expensive process than using the blast furnace. So part 1, why is a different method used for aluminium? Well, aluminium is a more reactive metal. Okay, or you can say it is more higher on the reactivity series than carbon, or it is above iron on the reactivity series, any sort of thing implying that it would be more difficult based on its position in the reactivity series. Part 2, stating the major reason for the high cost of extracting aluminium, and it is due to the cost of electricity. So the electricity is going to cost quite a lot of money in order to extract the aluminium. So coke is used in the blast furnace and it contains carbon. Carbon is also used in the extraction of aluminium, but it is used for a different purpose. So in this case, the aluminium is not used as the reducing agent. What it is used for are your electrodes, because in this case, it's not going to react and it's going to be an inert electrode. And the extraction of aluminium can be represented by the chemical equation Al2O3, giving you 8,4Al plus 3O2. And we want to show what the half equations are. So we're going to split this down. One of them is going to be for aluminium and one of them is going to be for oxygen. So if we start with the aluminium, we know that we're going to have the aluminium as an ion because it is in aluminium oxide. And it has a charge of 3+. When it goes to be aluminium metal, we have to gain electrons here. Okay, so when it is gaining electrons, we write the electrons on the left-hand side. When we have our oxygen, we know that we're going to have oxygen as an ion here, and it is 2 negative. And we are going to be forming oxygen gas. Now, oxygen gas is a diatomic, so it is going to be O2. So I'm going to need to have 2 oxygen ions. And this time I'm losing electrons, so my electrons have to be on the right-hand side. And I'm losing 2 electrons for every 1 ion I have. So that must mean I'm losing 4 electrons in total. And there you can check your answer if you've been practicing those questions yourself as well. That's everything for Topic 2E, Extraction and Uses of Metals, for the triple course. If you have any questions, please feel free to leave a comment below, and we hope to see you back on the channel soon.